Okay, in this problem, a car is modeled as a single degree of freedom system vibrating in a vertical direction. It is driven on a road whose elevation varies sinusoidally. The peak to through depth is 0.2 meters and the distance along the road between the peak is 35 meters. The natural frequency of the car is 2 Hz and the damping ratio its stochastic system is 0.15. The damping ratio is 0.15. What is the amplitude of the vibration of the car at a speed of 60 km per hour? Problem is asking. Then the second part, if the speed of the car is varies, what is the most unfavorable speed for the comfort of its passengers? Okay. Okay, this is the problem. Let's see how to solve this problem. Okay. Then let me draw the diagram including all the detail first. Let's take this the car model. First of all, I am going to draw the car model, the M mass, then the stiffness of the stochastic system, and including the tire stiffness, that means resultant stiffness. I am going to represent by the spring, and the damping of the this is a problem of response of a dam system to a base excitation. Response of a dam system to a base excitation. This is a tire. Then the tire producing this kind of harmonic vibration. The sinusoidal harmonic vibration, it says sinusoidal harmonic vibration. Peak to depth height is equal to 0.2 meters. Peak to depth height. That means this height. That means this height is equal to 0.2 meters. That means this amplitude of the forcing base excitation amplitude is equal to 0.1 meters. So then what is the frequency? That means the problem is also saying the distance between the peak is equal to 35 meters. That means this two peak, this distance between the two peaks is equal to 35 meters. Okay, 35 meters. And also problem says the data is given omega system natural frequency omega n is given, that is equal to 2 Hz. Okay, so I'm going to convert into a radians per second, that is equal to 45 radians per second. 45 radians per second. So then this car is moving with the velocity that is in the first part 60 km per hour. 60 km per hour, that I am going to convert into again meters per second. So then 60,000 divided by 3,600, that is equal to 100 over 6 meters per second. In this much of speed it is moving with this much of speed, that is equal to 16.667 meters per second. This much of speed the car is traveling. So then first of all I am going to find the omega f, forcing function frequency, that means base excitation frequency. How to find the base excitation frequency? The lambda of the sinusoidal of the peak to depth height of the road is equal to 35 meters. So then forcing function frequency, that is when it is moving in the 16.667 meters per second. So what is the cycles per second? First there is convenient to calculate using cycles per second. Cycles per seconds. What is cycles per second? That means it is moving in the per second, it is moving in 16.667 meters. So its lambda is equal to 35. So that is equal to cycles per second, that is equal to 16.667 divided by 35. This is the cycles per second for this base excitation frequency. So then we can convert into a radians per second by multiplying 25. That means I'm going to 16.667 into 25 into divided by 35. That is the base excitation frequency in radians. That is equal to 2.992 radians per second. Okay, this data is given. So then in the last lectures we discussed how to obtain the equation, chaotic equation for this described in this motion. Actually let's take this is the y dot. Then let's take because of this y dot there is moving in the x dot velocity. During when discussing the lectures we obtain the chaotic equation for this motion of this kind of m mass by applying the f is equal ma. F is equal ma to the considering the motion of m mass. We got this equation. You may remember x double dot plus cx dot minus y dot plus k x minus y is equal to 0. X minus y is equal to 0. So then this equation we can rearrange mx double dot plus cx dot plus kx, that is equal to cy dot plus ky, and there is in the right hand side part is equal to c omega y into cos omega t plus k y sin omega t. Okay, ky sin omega t. That means this base excitation we can represent by a this function base excitation yt function is equal capital Y into sin omega t. In this situation yt is equal base excitation for the function frequency is equal 0.1, the amplitude of the base excitation sin 2.997 into t. Okay, this is the base excitation function y. So then when discussing the lectures we discuss how to solve this differential equation. Actually it's a non-homogeneous second order constant coefficient differential equation. So then it's having the particular integral solution and the complementary function solution. The complementary function solution damped out in a few moment, after initial few moment, only remaining steady state vibration. That means we are interested about the steady state vibration of the system. Xt we can represent by x cos omega t minus 5. Here the x mean steady state vibration of the m mass. X mean the steady state vibration of the m mass. Okay, then by substituting this solution in this differential equation we can find the x. In the lectures we obtain this x value, that is what is the value for the x. We got this is equal to 1 plus 2 zeta omega divided by omega n into square divided by 1 minus omega divided by omega n into square plus 2 zeta omega divided by omega n into square root of total n into y. This is the x we obtain by substituting this solution in this differential equation. So then now I am not going to obtain this equation. I am going to use this equation to solve this problem. Okay, then what is our frequency ratio? So I am going to directly substitute the problem is asked to find the what is the amplitude of vibration. That means x, problem is asking the x. So I am just going to substitute these values in this equation. Okay. Then what is omega divided by omega n? What is omega divided by omega n? Omega divided by omega n frequency ratio. What is omega? 2.992 divided by omega n 45. So if we simplify this value, we are getting it is equal to 0.238. Then what is theta? Theta given in a problem as a data, that is equal to overall theta value, that is equal to 0.15. So then we just want to substitute these values in this equation, then we can get the x value. Okay, let me substitute these values. First of all, I am going to write the equation. X is equal 1 plus 2 theta omega divided by omega n into square divided by 1 minus omega divided by omega n into square plus 2 theta omega divided by omega n into square the square root of total into y. Okay, so then I am to substitute these values. X is equal 1 plus 2 into 0.15 into 0.238 into square divided by 1 minus 0.238 into square plus 2 into 0.15 into 0.238 into square root of total into 0.1 y. Okay, this is the one we are getting. So then I can simplify this equation. I have already have values of simplification of this equation, so I just write these values. That is equal to by simplifying this equation, finally we are getting 0.1059. That means that is equal to 0.106 meters for the amplitude of vibration. Okay, then problem in the second part. If the speed of the car is varies, what is the most unfavorable speed for the comfort for its passengers? That means this speed of car is varying. The speed of the car is varying mean what it means? We are varying the base excitation frequency. If you are varying the car speed, mean if you are varying the car speed from 0 to upwards, what it means? We are varying omega from 0 to upwards. Okay, 0 to upwards. So what happens when vary the omega in frequency ratio in from 0 to upwards? What happens? You may remember this graph when we are discussing the theory classes. We obtain actually this graph, the omega divided by omega n, the frequency ratio. That means here the displacement transmissibility. dt m, displacement transmissibility m. That means that is equal to x divided by y. That is called the displacement. That is equal to x divided by y. That is called the displacement transmissibility. So then you can remember that how it vary. This is equal to 1. Then you can remember that one. Let's take this is the frequency ratio is equal to 1 situation, omega is equal omega n situation, then the square root of 2 situation, You can remember this graph we obtained in when discussing the theory classes. We obtained this graph. So then how it vary? For theta is equal 0 situation, it in the vertical asymptote, it goes like this. So it comes from the infinity, then it goes like this. Okay. So if any value theta is having the certain value not equal to 0 situation, it having this kind of a curve. It having this kind of curve. Okay. Then let's take this is the theta is equal 0 situation. Let's take this is a certain value, the theta is equal to, let's take the problem that is says 0 plus 1.5 situation. You can see the maximum displacement transmissibility occurs somewhere in here. Maximum displacement transmissibility occurs somewhere in here. This is the point where the most unfavorable point, because the maximum amplitude is transmitted to the body of the vehicle in this situation. So the problem is to find this omega value. Okay, this is the maximum transmissibility occur. The problem is to find this omega value. So let's see how to find this omega value. When discussing theory, we obtain the equation where maximum transmissibility occur. In where the maximum transmissibility occur, maximum transmissibility occurs at omega is equal omega n 2 theta 1 plus 8 theta into square root minus 1. Okay, then this is where the maximum transmissibility will occur. This we can easily find by derivating this equation with respect to the frequency ratio. Then we can get the maximum value for this function. Okay, maximum value for this function. So then anyhow we are in the equation. Here I am going to find the omega value, which gives the maximum transmissibility. Okay. So then if we can find the omega, then we can easily calculate the speed of the vehicle. So let's see how to find the omega. So omega n is given as the data 451 divided by 2 theta means 0.15, then 1 plus 8 into theta square 0.15 into square root minus 1 into half. So I have already calculated this value. I have the value that is equal to 12.3038 radians per second. But it means it produces this much of radians per second. So then how to calculate the cycles per second? That means in hertz. So I'm going to convert it into a cycles per second. How to find the cycles per second? The t is equal 25 divided by omega. So then 1 over t is equal frequency in hertz. That means omega divided by 25. In this situation, omega divided by 25, 12.3038 divided by 25. So then cycles per second in hertz that is equal to 1.958 hertz. 1.982 hertz. So then what is the speed of the vehicle? Speed is equal v is equal f into lambda. So then the v is equal f. What is the f frequency? 1.9582. What is the lambda? 35 meters. That means the road, the sinusoidal this value 35 meters. So then v is equal, we are getting 1.958 into 35, that is equal to 68.53 meters per second. So then we can convert into a kilometer per hour. 3600, that is equal to 246.7 kilometer per hour. That means in this speed, the maximum the transmissibility occurs. That means maximum displacement is transmitted to the mass. That is the most unfavorable point for the passengers. Okay.